8 things to know about NASA's mission to an ocean moon of Jupiter. The first NASA spacecraft dedicated to studying an ocean world beyond Earth, Europa Clipper, aims to find out if the ice-encased moon Europa could be habitable. NASA's Europa Clipper spacecraft, the largest the agency has ever built for a planetary mission, will travel 1.8 billion miles, or 2.9 billion kilometers, from the agency's Kennedy Space Center in Florida to Europa, an intriguing icy moon of Jupiter. The spacecraft's launch period opens in October 2024.
Europa is a moon of Jupiter, about the size of Earth's moon, which has an icy surface that probably hides a subsurface ocean.
Data from previous NASA missions has provided scientists with strong evidence that an enormous salty ocean lies underneath the frozen surface of the moon. Europa Clipper will orbit Jupiter and conduct 49 close flybys of the moon to gather data needed to determine whether there are places below its thick frozen crust that could support life.
Scientists think Europa has the key ingredients to support life as we know it. Number 1, water. Number 2, energy. And 3, essential chemical building blocks.
Here are 8 things to know about the mission. 1. Europa is one of the most promising places to look for currently habitable conditions beyond Earth. There's scientific evidence that the ingredients for life, water, the right chemistry and energy, may exist at Europa right now. This mission will gather the information scientists need to find out for sure. The moon may hold an internal ocean with twice the water of Earth's oceans combined, and it may also host organic compounds and energy sources under its surface. If the mission determines that Europa is habitable, it would mean there may be more habitable worlds in our solar system and beyond than we have imagined. 2. The spacecraft will fly through one of the most punishing radiation environments in our solar system, second only to the Sun's. Jupiter is surrounded by a gigantic magnetic field 20,000 times stronger than Earth's. As the field spins, it captures and accelerates charged particles, creating radiation that can damage spacecraft. Mission engineers designed a spacecraft vault to shield sensitive electronics from radiation, and they plotted orbits that will limit the time Europa Clipper spends in most radiation-heavy areas around Jupiter. 3. Europa Clipper will orbit Jupiter, studying Europa while flying by the moon dozens of times. The spacecraft will make looping orbits around Jupiter that bring it close to Europa for 49 science-dedicated flybys. On each orbit, the spacecraft will spend less than a day in Jupiter's dangerous radiation zone near Europa before zipping back out. 2 to 3 weeks later, it will repeat the process, making another flyby. 4. Europa Clipper features the most sophisticated suite of science instruments NASA has ever sent to the Jupiter system. To determine if Europa is habitable, Europa Clipper must assess the moon's interior, composition, and geology. The spacecraft carries 9 science instruments and a gravity experiment that uses the telecommunications system. In order to obtain the best science during each flyby, all the science instruments will operate simultaneously on every pass. Scientists will then layer the data together to paint a full picture of the moon. 5. With antennas and solar arrays fully deployed, Europa Clipper is the largest spacecraft NASA has ever developed for a planetary mission. The spacecraft extends 100 feet, 30.5 meters, from one end to the other, and about 58 feet, 17.6 meters, across. That's bigger than a basketball court, thanks in large part to the solar arrays, which need to be huge so they can collect enough sunlight while near Jupiter to power the instruments, electronics, and other subsystems. 6. It's a long journey to Jupiter. Jupiter is on average some 480 million miles, about 770 million kilometers, from Earth. Both planets are in motion, and a spacecraft can carry only a limited amount of fuel. Mission planners are sending Europa Clipper past Mars and then Earth, using the planet's gravity as a slingshot to add speed to the spacecraft's trek. After journeying about 1.8 billion miles or 2.9 billion kilometers over 512 years, the spacecraft will fire its engines to enter orbit around Jupiter in 2030. 7. Institutions across the US and Europe have contributed to Europa Clipper. Currently, about 1,000 people work on the mission, including more than 220 scientists from both the US and Europe. Since the mission was officially approved in 2015, more than 4,000 people have contributed to Europa Clipper, including teams who work for contractors and subcontractors. 8. More than 2.6 million of us are riding along with the spacecraft, bringing greetings from one water world to another. As part of a mission campaign called Message in a Bottle, the spacecraft is carrying a poem by U.S. Poet Laureate Ada Limon, co-signed by millions of people from nearly every country in the world. Their names have been stenciled onto a microchip attached to a tantalum metal plate that seals the spacecraft's electronics vault. The plate also features waveforms of people saying the word water in over 100 spoken languages.
Over the past 50 years, we've relentlessly searched our cosmic neighborhood, seeking the ingredients of life. We sent robotic rovers to Mars to drill into rocks. We skimmed the atmosphere of Venus in search of water, and even returned samples of water collected from asteroids. Despite these successes, we've not found the ingredients of life. Our next hope for finding the origins of life sits inside this Falcon Heavy, looking for life in a new environment. The icy moon of Europa. At first glance, Europa seems like an odd location to look for signs of life. Jupiter is outside the habitable zone of our solar system. Europa is a moon, just a little smaller than our own. Moons tend to be rocky, with little to no atmosphere, and rarely have a magnetic field strong enough to protect them from solar radiation. This is even a harsh environment for an orbiting satellite. Europa is solar-powered, but its panels will receive 4% of the light it would near Earth. But its problems don't end there. Jupiter's powerful magnetic field diverts and concentrates the sun's radiation, and Europa orbits within this radiation belt, exposing it to intense radiation that would fry a satellite's electronics in less than a day. So, why is NASA spending $5 billion to send a probe in search of the ingredients of life on Jupiter's icy moon? Let's take a closer look at the Europa Clipper mission and why it might just change how we look for life outside our pale blue dot. We have long thought that Europa has the potential for life, stemming from our suspicions of the presence of a large ocean beneath its icy surface. The first direct confirmation of water on Europa came from the Voyager probes, capturing these incredible images of the moon's surface as they flew by 250,000 kilometers away. Europa's surface was smooth and craterless, but marked with long ridges formed from what we thought was moving ice. These images ignited scientists' imaginations, and more missions like Galileo were sent to Jupiter, gathering incredible photos and data. However, some strange things started to happen to Galileo during its mission. It lost valuable data from close approaches to Io, one of Jupiter's other moons. High-energy electrons penetrated the spacecraft, altering a single bit of memory and causing it to enter safe mode. Galileo had stayed too long inside Jupiter's radiation belts, and its instruments had endured 3 times the radiation they were designed for. This radiation would make life as we know it impossible on Europa's surface. This is why Europa's icy shell is so important. It protects the ocean below from ionizing radiation. But, strangely, this radiation may be key to Europa's potential habitability. The plasma and charged ions that bombard the surface can create strong oxidants like hydrogen peroxide. If these oxidants make their way into the ocean below, they can react with other molecules, creating a slurry of different molecules that life can appropriate. Europa's close orbit to Jupiter provides it with energy vital for life in other ways too. Europa's eccentric orbit creates an oscillating tidal force that contracts and expands the moon. The friction this creates could heat up the water enough to sustain life in a relatively warm ocean. So how do we know this ocean exists when we can only see the surface? Because of Europa's strange magnetic field that Galileo detected with its magnetometer. The magnetometer consists of a base coil wrapped around a metallic ring core. On one half of the ring, the wire coils clockwise, and on the other half, it is wrapped counterclockwise. Another measuring coil is placed on top of this ring to measure the magnetic field running through the core. Without an external magnetic field, the magnetic field generated by these opposing coils would cancel each other out. But when placed inside a magnetic field, the core has a slight bias in the external field's direction. This can be sensed by the outer windings and measured as an electric current, allowing us to detect magnetic fields with precision. This magnetometer measured a strange deviation in the magnetic field surrounding Europa that could only be explained by a subsurface ocean full of dissolved ions. It detected an induced magnetic field caused by Jupiter's incredibly powerful magnetic field, which is 20,000 times stronger than Earth's. Jupiter's magnetic field is interacting with this salty ocean and allowing Europa to produce a field of its own. But an even stranger anomaly was picked up by Galileo on two of its orbits in 1997 and 2000. As Galileo was nearing its closest approach to the moon, the magnetometers picked up a large spike in the changing magnetic field, something our models of its magnetic field could not predict. It wasn't until 2014 that scientists began to put the clues together. Hubble took this image of Europa, showing a 200-kilometer-tall eruption. After extensive modeling with modern tools, they realized that Galileo likely flew through two of these plumes of ionized salty water. This is why the Europa Clipper mission is so exciting. Europa is such an oddity, and there's so much more to learn. We don't know how thick the ice really is, and whether it's thick enough to protect the inner ocean from the radiation belts. We've assumed that the tidal forces generate enough heat to heat the inner ocean, but we haven't measured how much the moon flexes and contracts by. These are just some of the questions Clipper is being sent to answer, but it has been designed for so much more. The original plan for Clipper's journey was to take a direct route to Jupiter aboard the SLS. However, due to a lack of available launches with the SLS and its expensive price tag, NASA switched to the Falcon Heavy. Although this saved NASA $1.5 billion in launch costs, the Falcon Heavy's lower thrust means it cannot take the direct 3-year route to Jupiter. Instead, it will be taking a longer route, passing by Mars and Earth for gravity assists. The first challenge Clipper will face is inserting itself into its peculiar orbit to avoid the worst of Jupiter's radiation belts. It can't simply orbit Europa. Doing so would decrease the life of the probe from the planned 3 years to a little over a month. Instead of orbiting Europa, Clipper will orbit Jupiter in a highly elliptical orbit. Every 14 days, Clipper will dive into Jupiter's intense radiation zone, speeding up to 4 kilometers per second as it flies by Europa. During this brief encounter, it will focus on collecting vast amounts of data. Then, Clipper will retreat to a safer region for 10 days, shifting its energy use to its communication systems to send back data and await any necessary orbit corrections. Clipper is designed to resist this brief encounter with the radiation belts. Tucked inside the main body of the probe, there is a large aluminum box. This is where all the electronics are stored. NASA calls it the vault. The engineers behind Clipper's vault modeled the radiation that the probe will be exposed to, and together with the mission planners, balanced the need for close approaches to the moon with time spent inside the radiation zone. Together, they worked to constrain the thickness of the aluminum vault walls to 1 centimeter to minimize weight. With space limited inside this radiation shield, the engineers had to play a delicate game of Tetris, carefully placing each instrument's chip on different panels. Clipper has 3 magnetometers to investigate Europa's magnetic field and gather more information on the nature of the subsurface ocean. By positioning them like this, we can get a measurement of the magnetic field in all 3 directions. However, the engineers needed to consider how the metallic structure of the probe could alter the readings. To move sensors away from the ferrous materials on the spacecraft, They created this unique coiled lightweight carbon fiber boom. This shape allows the 8.5-meter-long boom to be compressed into a small container. The natural flexibility of the carbon fiber creates enough force for the boom to deploy itself without the need for any actuators. The sensors are spread out along this boom to prevent them from interfering with each other too. They will give us even more data on the strange magnetic field surrounding Europa, and this will give us an even better idea about the nature of the subsurface ocean. But scientists are hoping that Clipper can gather material directly from the ocean, from orbit, by flying through another eruption, this time intentionally. When passing close to the moon, this lid opens to reveal a 25-centimeter wide collecting area. Dust particles enter and pass through a series of conducting meshes, altering their capacitance. This change is detected and used to measure the particle speed, helping to pinpoint their origin along Clipper's path. The particles move much slower than Clipper's 4 kilometers per second. As a result, the metallic back of the detector slams into the particles with enough force to break them into base elements and ions. An electric field at the back of the cylinder acts like a mirror, deflecting these ions into a detector. Heavier ions take longer to reach the detector than lighter ones, and by measuring these time-of-flight differences, we can identify the dust particles' building blocks. But dust particles are not the only thing that Clipper will encounter. The probe will be close enough to the moon to sample the composition of its tenuous atmosphere too. We want confirmation that the radiation raining down on the ice creates gases that are needed for life. As Clipper flies low in Europa's atmosphere, gases enter this tube and are bombarded with a stream of electrons. This removes electrons from the gas molecules, ionizing them. The charged ions are then propelled through an electric field that accelerates them. Ions with different masses accelerate at different rates. Heavier ions move slower, and lighter ions move faster. These paths lead to an electronic detector that counts the ions. This data will tell us about the compounds present in the gas of Europa's atmosphere. If Clipper does not pass through the plumes, it will still analyze the moon's surface composition using light. 2 instruments will be used for this analysis that cover the infrared and ultraviolet spectrums. We will be measuring Europa's gravitational field too. You may have seen this picture of Earth's gravitational map. It shows where mass is concentrated on Earth. This was measured using 2 identical satellites in a polar orbit, one further ahead than the other. When the leading satellite encounters an area of stronger gravity, it is pulled slightly ahead of the trailing satellite. This increases the distance between them. After passing the anomaly, the leading satellite slows down, while the trailing satellite speeds up, and then slows down over the same spot. These changes in distance, coupled with precise positioning from GPS instruments, allow scientists to create a detailed map of Earth's gravity. Clipper will do the same by measuring the changes in speed. But the challenge lies in accurately measuring the acceleration and isolating Europa's gravitational force, all from Earth, without a second satellite. Acceleration will be measured by pinning down the change in velocity of the probe over time. We can send an 8 GHz wave to the probe. Depending on its velocity relative to Earth, it will receive a different frequency. If it's moving towards Earth, the frequency it receives will increase, and it will decrease if it's moving away. From the shift, we can determine the velocity of the probe with an accuracy of 0.1 millimeter per second. However, this method relies on a direct line of sight between Earth and Clipper, and the measurements can only tell us the probe's velocity with respect to Earth. With Europa orbiting the largest planet in our solar system, we will lose sight of it. The end goal of these gravitational measurements is to quantify how much the moon squishes and stretches throughout its orbit, not just a static moment in time. The team estimates that they will need almost 10 passes to get the measurement below the uncertainty threshold. What the public are probably most likely excited to see are the images that Clipper will provide us. Clipper is carrying 2 8-megapixel sensors, one with a wide-angle lens and another with a narrow-angle lens. Over multiple flybys, Clipper will cover 90% of the moon, allowing us to see details with a resolution of 100 meters per pixel, which is 6 times more surface area with 5 times better resolution than the best images obtained by the Galileo spacecraft. While we don't think the ingredients of life are just sitting on the surface, The camera system will inform scientists of the dynamic behavior of the moon, something that is quite unique in the solar system. Understanding the ways the ice shifts, how it piles up, or how it gets pushed away could pinpoint where in Europa life could happen. While the cameras are busy taking pictures of the surface, a radar sounding system will start looking and measuring the thickness of the ice below and any elevation changes. To effectively penetrate Europa's ice, the radar will use two frequencies, a shorter 60 MHz wave and a longer 9 MHz wave. The longer 9 MHz waves can travel through the ice without being disrupted by rough patches. However, radio waves from Jupiter interfere with the signal, limiting its use to the side of Europa facing away from the planet. The shorter 60 MHz waves are not affected by Jupiter's interference, but are more prone to disruption from the roughness of Europa's ice. NASA has plenty of experience with this technology, with satellites monitoring the thickness of ice sheets here on Earth as the planet warms. To power all of these scientific instruments, NASA made a counterintuitive decision. If you compare all the probes that have gone to Jupiter, two of them stand out. Juno and Clipper are the only ones with large solar panels. All of the previous probes were built and launched at the height of the nuclear arms race. A byproduct of the nuclear warhead production process is plutonium-238. This isotope of plutonium is not useful for bombs, but the trash of the Department of Defense is the treasure of NASA. Plutonium-238 is the perfect material to use as a nuclear fuel for space probes. Its half-life of 88 years makes it radiate fast enough to produce a constant heat source, but not so fast that it would deplete itself on longer missions. The radiation it does emit are also large alpha particles that are easily absorbed and converted to thermal energy. Plutonium is manufactured as plutonium oxide pellets, which are a ceramic material. Each pellet is 5 centimeters across and 10 centimeters tall. If anything were to go awry during launch, the nuclear fuel would not burn up or turn into powder. Its chunks would break up and simply sink to the ocean floor. In 1968, a weather satellite using plutonium-238 as fuel blew up during launch, but its fuel source was recovered from the ocean floor, refurbished, and put on the next mission. But since 1988, when the US stopped its nuclear warhead production, NASA has had to rely on its own stockpile of plutonium-238 and has had to buy some from Russia too. By the early 2000s, when Juno was being built, both NASA and the Russian stockpiles were running low, so the little plutonium that was left was prioritized for other missions, mainly to Mars and the Moon. So Juno had to rely on solar panels and use batteries to store what little power there is to survive the regular eclipses behind Jupiter. The European Space Agency lacks nuclear power space capabilities, so their Rosetta, the probe that landed on a comet, had to rely on solar power instead. Seeing both the success of Rosetta and Juno, NASA was hesitant to use nuclear power generators on Clipper, instead giving it 30-meter solar panels. Plutonium-238 has helped NASA to be at the forefront of space exploration, but the US national stockpile of the material is dwindling. The only confirmed plan to use plutonium in a space mission is on Dragonfly, the flying vehicle that will explore Saturn's moon, Titan. Scientists have been sounding the alarm for the low stockpile of plutonium, and in the last 10 years, the US government started to ramp up production of the material at the Oak Ridge National Laboratory. The current rate of production of 400 grams per year would require 10 years to replace the 4.8 kilograms that the Perseverance rover needed. Automations in the production process will help ramp up that production rate to 1.5 kilograms per year.